All right. Well, bad one to miss too, to be honest. Ugh. We're hitting some pretty big things. All right, we were doing string trivia. So this is where we ended. It was this idea that letters are actually, they have numbers associated with them. Now, I want to be clear about something. I mean, maybe arbitrary is not the right word, but it's arbitrary. There's this thing called an ASCII table. And it basically shows you how actually, it's important to be careful about what we're seeing here. What it's showing you is that the binary encoding for something like the letter lowercase a near the top right there is the same as the encoding for the number 97. Now, I'm not saying that the letter A is 97. I'm saying that the bit string, like the patterns of zeros and ones that mean the number 97, also mean the letter A. However, let me show you. 97 in binary. So the number 97 in binary is 0, 1, 1, 0, 0, 0, 0, 1. Actually, there's like an infinite number of zeros ahead of it, but I wanted to say 8 unique bits. So that right there, that OB, that just means like it's binary. Okay, so the thing that matters is this part right here. Here. There. That's 97 in binary with 8 bits, 1 byte. But that right there, that series of zeros and ones also means the character A, lowercase a. And it's because information, like a number, is encoded, or a string, or an individual character, is encoded in binary, just like everything else is encoded in binary. But what that encoding means depends entirely on how it's encoded. Really, actually, I should have said decoded. The number 97 is encoded as 011000001. The lowercase letter a is encoded as 011000001. It's encoded the same way. But if I were to give you just that number right there, that binary pattern, and I were to say to you, what does it mean? You can't answer that question. You have to answer. You have to ask me, well, what am I decoding it to? Is it a pixel? Is it a color? Is it an individual character? Is it a number? What is it? And until you know what information, what type of data it is, you have no way to know what that really means. That's just an encoding. You might say to me right now, well, look, sure, like, okay, the binary encoding for the letter A is like arbitrary, someone picked it, right? But like the binary encoding for the number, I guess 97, that's its encoding in binary. Like that's just the way it is. So it's not really arbitrary, except it is, because the number 97, you're thinking too much as a human. You got to think it's just the number 97 has no natural encoding. It's just the number 97. It's this abstract idea that we encode one way or the other. So at the end of the day, these are just encodings that have meaning when we decode it. And the same thing is true for everything in our life too. Like we encode information in certain ways and then we decode it to mean something. So the number 97, 011000001, and the letter A are encoded to the same thing, but the way to decode it depends on, like, we need to know what we're encoding. If I were to say 97, or the individual letter A, if we encode it, it gets encoded. They both get encoded to 0, 1, 1, 0, 0, 0, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. But if I didn't tell you, really what I'm saying here is to hit the point hard, is if I didn't tell you, like if I were to say, okay, here you go, what does this mean? You don't know. You just have an encoding. And until you know how to decode that thing, you can't tell me. So every letter really is can really be mapped to a number, and every number can be mapped to like a character. Now some of the characters are like, they don't really say, like if I were to say the number 33, well that's exclamation point. The number 17, well that actually doesn't really have any meaning. The number, let's see if I can find another one. The number 10 is like a new line. The number 35 is like the number sign. They have the same encoding. And this really goes back to like, at the end of the day, as far as the computer is concerned, all of this information is just low voltages and high voltages. We have no way to know what those low voltages and high voltages mean unless we have a system of encoding things to the low voltages and high voltages, and then decoding things from the low voltages and high voltages to mean something. It could be an integer. If I were to go open up my RAM and go look at something, and I can see all these like potential differences in there, and oh, what am I looking at? I have no clue. Without having there's no way for me to know without having a system to tell me how to decode it. Interestingly enough too is the zeros and ones must be encoding information, right? Like they must be encoding like strings or integers. But the zeros and ones must also be, now, I mean, mind you, this is all technically information, but the zeros and ones must also be encoding instructions, right? The zeros and ones must be able to mean things like a number or a string, but they must also be able to say like for loop, right? They must, which is interesting. But that's well outside the scope of this course. All right. F strings. So this one's really nice, F strings. Not all these languages out there are as enlightened as Python in terms of how easy it makes making nicely formatted strings. If you are making a string, so remember how if I were to say, if I wanted to, here, let me show you what I mean. Of course. Connecting. If I were to say, there. If I hit run, this won't work, right? Not a big deal, because there's this easy solution. Okay, yeah, you can't concatenate a string with an integer, but we can convert the integer to a string. And whatever, it'll work nicely. Huh? Oh, there. Even more to prove the point I'm about to make. Right, so here you go. I can make it work. But this is a little cumbersome. It's not crazy, but it's a little cumbersome. It's prone to errors like the one I literally just did, not intentionally. So instead we could do something called like an F string, where what you do is you put a little F in front of it, and in the context of an F right before string, it has special meaning. And then here, you don't even need to start concatenating strings, because Python will do all that for you in the back end. You add these little, like, we call these braces, the squiggly brackets. They're called braces. You put those where you want it, and then you can put the thing you want. And then you hit run, and it works fine. It's a little bit nicer, it's a little nicer way to format your strings like this. If you don't like it, you don't have to do it. If you like it, you can do it. It's great. I recommend it. It's pretty much it's like what everyone does these days. It's nice. And it actually gives you a couple of, now there are a lot of different ways actually to format strings nicely in a computer. Some of which are old conventions and styles people made like 50 years ago that still kind of kick around today in one way or another. But these F strings are a little bit more modern, let's say, for lack of a better word. So here's an example. My name is name, and I love course code, right? You can put in whatever you want, as many variables as you want. These are clearly examples of embedding strings inside of strings, but we could do it with numbers. And what's nice here is you can even do things like say, okay, I've got a float, 456.789. But if I really only care about showing 2 decimal places, I can do this. :.2f. Now, no one in their right mind, unless you do this enough that you just memorize it because you do it enough, no one in their right mind would expect me to tell you this right now and you to be able to remember that off the top of your head. No, you just go like, I know there's a way to format these strings nicely with F strings in Python. I'll just look it up and then you'll see a list of a billion different things you can do. So that's nice if you're dealing with something like prices and then suddenly you get like fractions of pennies, right? I don't want 3 decimal places with my dollars. I only want 2 because you can only break a dollar down into a cent, right? So some float :.2f means, well, we got a float and I only want 2 decimal places. Cool. You can even do, like, here's an example. Look how ugly this is. Oh, this is hideous. I'm showing you right there. If I were to run that, that's the output I would get. I put it in a comment, but if I were to run it, that's what I would see. Now, if you get like your little bill or like your receipt, would you ever get something where like the decimals don't line up? No, of course not. Everything would be aligned really nicely on the decimal, right? What I mean here is, see how like let me show you. See, the decimal's under the 0. Wouldn't it be nice if it was under here and then, oh my God, this one's way over there? What a problem, right? It's terrible. Well, there's an easy way to do it. You can say, okay, each string is going to take up a total of 8 characters, and 2 of those characters will be decimal points. Effectively, you get that. Oh, isn't that beautiful? Wow. Now, like I said a moment ago, no one in their right mind, like, this isn't on the test type thing, right? Like, oh, write down the fancy symbols to make it print things out nice. No, that's psychotic, because if you needed to do it, you would just figure out how to do it. The goal that you have is you know enough that if you had this problem, you can solve it. That's the takeaway here. Oh, and by the way, going back to the ASCII table, just to be very clear, look, the number 0 is actually the same as the number 48. And 1 is 49, and 2 is 50, obviously. Right? Isn't that nice? By the way, there is method to the madness on this. I said it's arbitrary, and ultimately, it kind of is, but it was like intentional. There was an intention why this ASCII table was laid out the way it was. And I always thought it'd be really interesting to have like a course on like the weird history of computing and how we end up with shit like this today, where you're like, but why? And it's like, well, there was a reason. It doesn't really make sense today anymore, but good luck undoing 50 years of technology. So there's a lot of interesting things like that. Yeah, okay. So yeah, this is obviously only showing you I'm scratching the surface of F strings. If you ever think, how am I going to do it? Don't worry, Google exists. As an example, Python F strings. Oh my God. Man, it doesn't say anymore. It used to say like, I found you 10 billion responses in half a second. It doesn't say that anymore. but you'll find your answer. If it's answerable, someone's answered it. Now, here's where the people that aren't here today are screwed. Objects. I'm about to change everything. What I'm going to cover right now is only teasing. Kind of showing you where we're headed. Everything we're about to do now is going to be related to objects, but we're going to be able to talk about objects at a little bit of a higher level, so we're not going to be spooked by them. But in a couple of weeks, we're going to really be opening these things up and hacking around with objects. But now it's critically important to make sure we are clear about what objects are. So, when I'm talking about objects, really I'm going to be speaking like more traditionally speaking. Python does things a little differently, but it's still actually, Python goes out of its way to pretend it's doing things the traditional way. This is just to hedge against some asshole that's going to, tell me that, well, technically in Python, everything's, I know, but it doesn't matter right now. So, traditionally speaking, we have things like primitive types. Your booleans, your floats, your integers, your individual characters. Those are primitive types. They're simple, they're nice. I know how much room they take up. They each fit in a nice chair in this room. It's great. They all fit in a RAM nicely. If you give me an integer, I know exactly how much room it's going to need in the computer. But we saw strings are weird. If you give me a string and you say, hey, go put this string in RAM, I go, not so fast. How big is it? I can't fit a string in one seat. Does the string have 5 letters in it or 5 million letters in it? They're obviously going to take, one's got more information in it. I need more room to store that information. And this is where objects come in. Objects are this you take a step back from a type, and it's a type, it's information, but it's got a lot more bells and whistles involved with it, like a string. And with objects, object-oriented programming, was all the craze 30 years ago. And it still is, but today people are a lot more cautious about it than they used to be. People thought this was the greatest thing on the world, and then people started to quickly realize, I don't know, maybe we got to take it easy. There's nothing wrong with object-oriented programming. Python is technically an object-oriented programming language. Java is as well. A lot of the big ones are. And there's a lot of value in these things. But people misuse them a lot. But that's a topic for another day. For now, objects. I'm going to keep it very high level. We've seen things called primitive types, your integers, your floats, your booleans. But we've seen strings and how they're different, and strings are objects. We have also seen built-in functions. Things like print, absolute value, the square root function. Those are functions. And remember, a function is just a function. It's a piece of instructions that may or may not receive input and may or may not produce output. Strictly speaking, they better receive input and output. But, that's the idea, a function, okay? That's it. It doesn't care. So there are built-in functions. There are functions that are built in, but in the broader standard library, we had to do things like import math, right? And we even wrote our own functions, like character is in, right? Checking if the letter A is in blah. So there, we've seen these functions. However, there is a whole other weird category of functions that are functions, but they're not. But they are. But there's a catch. These are called methods. Raise your hand if you have experience in Java. A little bit. Okay, I've asked this before, but I'm curious. Okay, who here has had programming experience before this class? Okay, what language was it? Do you remember? Python? Python, HTML? Java and a tiny bit of C++. So with Java, technically in Java, there ain't no such thing as a function. There's no functions in Java. None. Everything's a method. Now we have static methods, which are totally actually functions, but they're not, but they are. In Python, we have both, depending on how we use these things. Now, I'm preloading. I'm giving you a lot of this stuff just to make sure you're paying attention and you're freaked out that something weird's going to happen. That's what I'm doing right now. It's really not that bad, but I'm making sure it's clear to you that these are different. They're the same, but different. So, here's an activity. We're going to do it together. Imagine for a second, though, I told you, write a function, listen carefully, write a function that takes a string and returns a new string, but all the letters are uppercase. Okay? Imagine I told you to do that. Don't actually do it because I'm not about to do it, but I'm going to show you like how we would go about do it. I would, okay, def make uppercase, and I would get like the string, it's a stir, and it returns a stir, right? And then blah, 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 and then after everything, right? That's the general idea of what it would be. I don't know what's going on in there, but okay, this is a function. It takes the string. It's going to make a new string that's all uppercase, and then it's going to return that new string, right? That's what it would look like. It's a function. That's what functions look like. That's how they work. Any questions about this? And yes, the question marks are, it's a stand-in for how would this actually work. That's not what's important right now. What's important is this is a function. Okay? Yeah? Happy? Sad? All right. Now, if that functionality exists already, I don't need to write that function because I have a method, or more appropriately, strings. String objects can be told to give you the uppercase version of the string. I'll show you what I mean. So this is obviously not going to work. Okay, A equals this is a string, and I love blah, 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 it. Cool. Right? Cool. Nothing spooky. There we go. It's just a string. But watch this. No, let's do. I said A, that was the variable that was storing the string. All right? See? On line 1 in that box, A equals whatever it was. And now I'm saying B equals A dot, and I type in the dot, and Colab's like, oh, here's all the things you can do. These are all, well, some of them are attributes, depending on the object, and some of them are methods. Methods are effectively functions. Now, let's have a look at them. Capitalize, case fold, center, count, and code, ends with, expand tabs, find, format, format map, index, is alnum, is alpha, is ASCII, is decimal, is digit, is identifier, is lower, is numeric, is printable, is space, is title, is upper, join, L just, lower, L strip, make trans, partition, remove prefix, remove suffix, replace, you get the point. There's a lot. There's capitalize. I wonder what this will do. Oh, why didn't it work? Did it modify? No. Oh, capitalize. Watch. You see what happened? Watch the first letter. Lowercase. When I go to B, because remember, strings are immutable. So I said to the string, hey, give me like a capitalized version of the string. I assume this was the uppercase one. It's not. It's capitalized. So it just, So I get the capitalized version of A. Well, that's just going to be, actually, I'm curious, what will happen if I do like, oops. No, only the first letter. So it gives me the new string, but the first letter is now in uppercase. Cool. Notice that when I print A out, though, A is left alone. It's B that's the new, different one. What else can we do? Upper. I don't know what this is going to, let's see. Yeah, there we go. Upper. So this is a method. A function takes parameters, or arguments, really. A function takes arguments, and methods could take arguments too. I'll show you an example. A dot find, no, count. You mean, can I do it on a literal? Yeah. You can do it on a literal. Yeah. There. So here's an example of a method that counted the number of i's in the string. Which string? The one that A had. So, well, let's see. 1, 2, 3, 4. I guess it does care about capitalization. Yeah, yeah. There's probably like an ignore case flag or something. So this one has an argument, but notice that, like, when I go back to upper, so there's still parentheses there like a function, but this never, like, if I wrote it as a function, I'd have to give this string to the function, and then the function gives me something back. Here, I never gave it an argument, yet the function, or method, gave me something back. It's because the method has what we call the implicit argument. The implicitness is, look, I said A. What is A? A is a string. A is not every string. A is a string, a specific string. It's the string, this is a string and I love blah, 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 blah. And when I said dot upper, it takes that one. You are all, and this is a really good analogy. I'm not straining here. You are all a human. All right? You all have a first name. You all have a last name, right? You all have some height associated with you, with eye colors, right? You have these like attributes, this like data, information associated with you. But you have a first name, and you have a first name, and you have a first name. You all have first names, but they're different, right? I mean, they could be the same, but they don't need to be. And I could say to you, raise your hand, raise your hand, raise your hand. You can put it down. Point being, I can act on individual objects. You are all objects now. I can act on all of you independently, and you will all act independently. Telling you to raise your hand was like a method. I told you to raise your hand, so you rose your hand. So a method really is very similar to a function, but it has an implicit argument, one that I didn't need to actually pass to the function because, well, the string knows what it is. Like, I didn't need to say, like when I said, hey, raise your hand, you weren't like, whose hand am I raising? It's yours, right? You're not doing that. You rose your hand because it's your hand. This will get clearer as we learn and see a lot more. We're going to make our own objects pretty soon. But functions, and methods are different. They're very, 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 very similar, but they are different. So, yeah. Now, okay, method versus function. Why do we do it with a method? Why a string.upper instead of some function, assuming it exists, called like upper a string? Well, there is nothing stopping us from having a function. But with the string, the sequence that makes up the strings are stored in that object. Like a string is a string that's like storing information, the string. So, like the method, when I say when I say upper, I'm telling the data within that object to do something. So it kind of makes sense from like a design and like code layout perspective. We're like, okay, I've got this upper function. Where should I put it? Just kind of like shove it in with the strings, because it's some functionality associated with strings, so let's put it with the strings. Why? It kind of makes sense from like an organizational standpoint. So like that's kind of why. So objects are these ideas where, you know, we have data and we have functionality, which at the end of the day are the same thing. Functionality is data, but let's not get into those weeds right now. We have data and functionality. Up until 1980, that's what we had. And then someone came along and went, wait a minute, let's do this. Let's put the data and functionality together. And since that time, we've been regretting it. But we can. There are some cases where combining this information is really nice. But what I'm going to do, I'm going to tell you right now. If this was, by the way, I don't know if you know this, it doesn't really matter what university you go to for computer science. You can go here or some other university, and you're going to get very, 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 very similar degrees, because we follow a fairly strict like guideline set up by like the ACM, which is some professional organization. Okay. I would put money on this version right here at St. FX has to be #1 or near the top in the country. For real, this version of 161 is so good. And part of it is because I've had a lot of like help from my friends that have been working in industry for decades, where a lot of professors are really insecure. And they hate people in industry because they can't possibly know what they've been studying forever, even though they probably know a lot more than the professors do. So I've been doing this stuff in practice for a long time, and they've been showing me all these things that are really great. And I guarantee you, you go down the street to some other university, and they're going to be talking about how great objects are. Look, you can combine data and functionality. Meanwhile, I'm telling you, like industry people are like, no, stop it. Don't do that. So what I'm going to do is I'll show you how you can use objects effectively. We're going to be using objects because that's the way the world is. We've got objects everywhere. But I'm going to show you how we're going to be very careful and very thoughtful and intentional with everything we do around our objects, and how we are going to very cautiously put our data and functionality together. The biggest area where we're going to see data and functionality combined with mutable stuff, we're going to get there very shortly, I'm jumping ahead a bit, is when we get to data structures. Because data structures are kind of like, well, that's like their whole shtick. But in general, we try to keep these things separate, and you will see a lot of examples of this. I will keep showing you for the rest of this whole year if you're taking 162. That's where it's going to be really obvious how we have objects that are really just storing data, and then we have objects that aren't going to store any data. They just have a bunch of functionality associated with it. I'll make it clear as we go. So I'm being very intentional how I'm showing you how to use these tools correctly, or effectively, let's say. So at the end of the day, now you're thinking, how am I going to remember what's a function and what's a method? You don't. Don't be silly. That's crazy. You look it up. How do I convert a string to uppercase in Python? Oh, there's a method. Okay, good. There we go. Yeah. That's how you do it. You don't. The only way I would, these are things I wouldn't say in general you're going to memorize. These are things There is some amount of this that you will memorize by virtue of just doing it enough. Like there are some of these tools that are so common that you just kind of know where they are because you've done it a billion times. That you're like, oh, okay, I know the string has an uppercase. I know I can ask a string to search it for a letter. Yeah. Any questions about that rant? Cool. All right, so lists. Now, we've seen lists before. We've talked about lists before, but we never really sunk our teeth into lists. So lists are like strings, or they're similar to strings in the sense that it's a collection of information. Where a string was a series of letters, a list is a series of just like arbitrary things, really. So it's like a string is a collection of characters, but a list can be a collection of whatever. So we're going to do this activity together real quick. Whoops. All right, sum list, 5, 7, 9, 10. I printed out some list, I got the whole list. I said, give me some list at index 0, well, that's 5. Give me some list from index 1 to 3, so that's okay. 0, 1, 2, 3. So that gives me 1 and 2, but excludes index 3. And tell me the type, well, it's a list. What am I going to see if I do this? It's not a trick question, you should be able to know. Hint. Well, some list is a list. Some list at index 1, well, that's the number 7. And what's the type of 7? Well, it better be an integer. Cool. We can get the length of a list in the same way we can get the length of a string. It's 4. What else we got? Can a list contain things of different types? Well, can I go in and do A? Yep. How about bool? No, that's a type. Well, apparently I can. True. What did I just add to the list at the end there? Let me make it more obvious. Yeah. This is a list where the index 0 is 5, 7, 9, 10, A, true, 1.1. Oh, a new list. I've got a list inside a list. That's entirely fine. You think I could put a list inside a list inside a list? Probably. What about a list inside 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 a list? Could I do that? Probably. I imagine there is a particular case where, like, yeah, that's really what you got to do. But in general, you're probably cheesing it pretty good, aren't you? Yeah, I've got a list inside a list. Yeah.
How would you identify the list inside of the list? Like, is there a way you could?
Well, I can ask the type, so I could be like, okay, some list at index, well, I happen to know. Well, okay, if I were to do a linear search, I could do a linear search on the types of things. Is the type of this thing a list? It is. Found it. But if you just want to confirm, okay, I know -1 is the last element. We don't, well, the last element has a length of 3, which is true. What about index 1's length? Well, that doesn't make any sense because the number 7 doesn't have a length.
How do you get like the second index of the last index?
Well, I bet you know, but let's have a look here. If, okay, A equals, okay, I have a list of 2 lists. I have one list where the contents of that one list is a list and a list. And the contents of those lists are just some numbers. Right? Now, I know I can do this, right? B equal, okay. If I wanted to get some element out of a list and store it in a variable, I could do this, right? X equals A at index 0, right? And print out X. Well, that gives me that whole list. And if I want to index something there, I can be like, well, give me the thing at index 1. Well, that's the number 1. Maybe this will be a little nicer, right? So A at index 1, well, that's this list. I stored that in A, and then I indexed, in X, pardon me. And then I indexed it like that. Or I could just do like that. Because A is the whole list. A at index 1 is a list. And then we can index lists like this. And print X. We see 3. Why? Well, A is this whole thing. A at index 1 is this whole list. And then the A at index 1 at index 0 is, well, that's the thing at the beginning of that list. If you're like, whoa, slow down, this should not confuse you. And if it is, you're going too fast. So you're right to tell me to slow down. But just make sure this makes sense later, because you're going to need to be doing a lot of this going forward. All right? Now, something interesting. Remember how like a string, I can say A equals like this, right? Print A, it's nothing, print type of A, and then print A. It's a string, but there's nothing there. The same thing could be true for lists. Whoop. We have a list. It's a list, but there's nothing in it. So we can have lists of length 0. Now, here's something that's funny about lists. Here's something funny about lists. Remember how with strings are immutable. We can't change them. Lists, on the other hand, we can. I can say at index 2 is equal to, I can go in and change the contents of the lists. We can do that. So a list is therefore, if it's not immutable, it is mutable. Nailed it, right? It's mutable. We can change it. For better or worse. A lot of people hate this. Usually people make an exception on mutability for things like your general purpose data structures, where the point is to be able to access and store and change data pretty frequently, like with a list. There are immutable versions of lists called like tuples, but we'll see those shortly. Another funny thing about lists is you can actually go to a list and say, append. We can append to a list. Now, notice that this is a method that didn't return anything. And how do I know it's a method? Well, I called it on a list. Some list, that's a variable that's for a list, right? The list A, B, C, D. And I told that list, hey, append to you the letter X. This is a method. And it modified the list that I told it to. If I had another list, some other list equals literally the same thing, notice that there's two lists, but I told the one associated with the variable some list to append X, but I never did anything to some other list. Is this clear? Now, I'm not playing. If this is not clear, ask me now. Because if it's not clear, you're certainly not going to be happy with what I'm about to show you. You're both a list, okay? And I'm going to tell you, you are both a list, but you're like clones of one another. Let's pretend you look exactly the same. You don't, but close enough. All right? They're clones of one another. You raise your hand. Did he raise his hand, though, the one on him? You did. You didn't. Why? Well, because no one told you to. See? They're separate. It's entirely fine, right? Happy? Sad? Give me a big thumbs up and a smile if you're happy. So tell me, what can we do to make this clearer? You can put your arm down. All right, well, if you're unhappy with this, maybe this will make you happy. Or maybe this will make you very mad. Check this out. Raise your hand if you're still happy. Really? Oh. Why are you happy with this? Before, how many lists did I have? I had 2, right? I had 2 lists. They were identical, but I had 2 lists. They were separate. Here, well, here, I only have 1 list, but I have 2 names for the 1 list. I have what we call an alias. There's 1 list. It's like my hand is the variable some list, and it's pointing at you. And then I create another variable that says, hey, some other list, point to the exact same thing. Okay, so I have 2 hands pointing at you. And if this hand says, hey, raise your hand, really high, everyone can see. As far as this hand's concerned, you raised your hand. Because there's only 1 you. Where before, you can put your hand down. Before, there were 2 separate things. Now I'm going to show you something even weirder. Let's get rid of some other list. Let's simplify that there. So we can append, great. What if we append like some list to some list? Whoa. What did I just do? Okay, hold on. What's some list at index 0? A. Some list at index 1? B. C. Oh, spoiler. C. 3. This makes perfect sense, right? What did I add to the list at the end? Does anyone know? When I appended something to the list, what did I add? What do you think? So I'm going to draw something real quick because I know we're out of time. I'm going to draw something to make clear what I did. When I appended to the list, I added something to the end. That's fine. But I had the list A. So I have a variable called some list. I'll just call it SL. That's like this, okay? It's a variable that gets me to this list. And the thing I'm adding to the end is actually what we would call a reference back to the beginning of the list. So that's what I've done. The thing at the end of the list is a reference that gets me back to the whole list. Yeah. What's the length? This is easy. The length is, no, the length is, you tell me what do you think the length is. Yeah, because this is still one thing. Yeah. Yeah. And on that bombshell, Have a great reading week. Oh, you got to wait a whole week to find out what the hell's actually going on.